Okay, so as our last topic in this lecture, let's talk about importance sampling. Okay, so in fact, let's use a very practical example in which we want to sample a hemisphere, directions from a hemisphere, but we want to prioritize directions that are more perpendicular. Okay, so think about this surface on which we want to compute illumination at this point. Okay, as always, we draw a hemisphere around our point that's going to be shaded, and with importance sampling, what we want to do in this case is we want to send out more samples in these directions. Okay, so we want to more sample these directions more densely than these more steep angles. Okay, so we still want to give these probabilities. We do not want to have zero probability for these angles, but we want to give more samples to the perpendicular directions. And this doesn't actually change anything in the formulation of the Monte Carlo integration. So if you remember, in Monte Carlo we were dividing the value of the function. So we were actually computing this 1 over n sigma I from 1 to n fxi divided by probability of xi. Okay, so this probability can be uniform probability for every xi, or it can be a non-uniform probability. It doesn't change anything in the formulation. Okay, but if we choose directions, remember one of the goals is to obtain images that are less noisy, which means images that have less variance. And if you remember, when the probability density function follows the real function which we are evaluating, we will have a smaller variance. Okay, so importance sampling tries to achieve that by using the same number of samples, obtain a less noisy image. Now let's talk about how we can do that. Okay, so normally from the previous video, what we had the following, right? We said P theta phi is equal to C. Okay, we wanted to theta phi to have constant probability. Okay, we want this to have constant probability. But we also had. I'm sorry. So this is not what we said. What we said was PW is constant. That's what we said, right? PW means every direction, every point on the surface of this hemisphere was equally likely. Okay, and if you remember, in using the Jacobian formulation, what we had was the following. We had P theta phi divided by sin theta was equal to PW. Okay, so this was the Jacobian of the transformation that maps theta phi to x, y, z points on the surface. Okay, so now replacing this with C and moving this to the right, we had this formulation. Okay, so from here we were able to find theta and how to sample theta and phi. Now in addition to this, what we want to do now is we want to, instead of this C being cosine, instead of this C being constant, now what we want to do is we want to have C times cosine theta. Okay, so which means that we want to provide more, we want to give more probability when cosine theta has a larger value. Okay, and cosine theta, because we are measuring theta with respect to this perpendicular axis, right? We are measuring theta with respect to this perpendicular axis. This probability density gives higher probability to vertical directions. Okay, so here I will just write, I will replace this with c times cos theta times sin theta. Okay, now almost like the same as before, but except we had this now cos theta term. Okay, so this is also known as cosine sampling the hemisphere. Okay, so let's first of all, let's find what this c is. How do we find it? Now I think we know how to do this by now. We integrate the distribution from in its domain. So c cos theta sin theta d theta d phi. Okay, I think you may have seen this integral before. This is supposed to give us 1, okay, for this to be a proper probability density function. But we know, I'm not going to drive this again, but we learned before that this integral actually evaluates to c times pi if you evaluate it. Okay, now c times pi is equal to 1, so from here c becomes 1 over pi. Okay, now let's clean this part. So now we know the following. Okay, from this derivation we have reached the following conclusion: p theta phi is equal to 1 over pi cos theta sin theta. Okay, now one of the things that we want to do was we want to write this as a separable probability density function, right? So this is now joint. Let's separate it. Let's say p theta phi is equal to p theta p phi. Can we do this? Now luckily it turns out that we can, but just we need to be careful. So we are going to say 1 over 2 pi here, okay? Because we know that 1 over 2 pi integrates to 1 in its domain. So we added 2 here. To compensate for that, we add 2 here. 2 cos theta sin theta. Okay? Now let me clean this part again. Okay? So here we can see this term actually represents our pi phi. Okay? P phi, and this term here represents p theta. So again, what this means is we have separated the joint density into multiplication of individual density functions, and again this can be done by using this trick. So we put 2 in the denominator and we put 2 in the numerator. They will cancel out each other and both become PDF. So important thing here to note is that this integrates to 1 in its domain, right? In its own domain, and this integrates to 1 in its own domain. What I mean by in its own domain is if you integrate 1 over 2 pi from 0 to 2 pi, you get 1. Okay? So d phi, you get 1. Okay? So this is a proper PDF in this case. Then if you integrate 2 cos theta sin theta from 0 to pi over 2, okay, d theta, again you get 1. Okay? So therefore we can treat them as individual PDFs. Now so the phi part is easy, right? So from here, this seems to be the same thing over and over again. So our samples, for selecting samples, the phi angle of the samples, we can simply say phi I is 2 pi our random number chi 1 I. Okay? This has been always like that. Now for the other one, what we do is we do our 3-step process. Okay, so we integrate, we first find the cumulative distribution, capital pi theta, or let's write capital pi x is equal to integral x from 0 to x 2 cos theta sin theta d theta. Okay, now this you can carry out this